On behalf of Panimala Institute of Technology, I welcome you all for ACTE Pre-Rana GATE Training Program for CSE students in the subject scheduled Database Management System. And the topic to be dealt in this session is normalization. So to start with, so in general, normalization allows us to organize the data in the database. Okay, so here we used to store the data as a database. So the database takes a form of table. So we can organize the data. So by using normalization is a concept or a technique or a process, we can say it allows us to organize your data in a well manner. Okay, so organization includes, so we can create tables and we can establish a relationship between the tables according to the rules designed. Okay, so whereas the rules are used to protect the data as well, that makes the database more flexible by eliminating the redundancy and inconsistency dependency. So in general, we can say that normalization is used to minimize the redundancy which are framed in your relation or a set of relation. Okay. Normalization divides the larger table into a smaller table. Okay, and links them using a relationship. Okay, so the solution. Okay, the solution to redundancy. So the redundancy removal is obtained by dividing the table, which is large in size, by dividing it into some smaller parts and making or establishing a relationship between them. We can make a solution which has a minimized redundancy. Okay, so we can say that normalization is the organization technique that helps to minimize the redundancy in your relation. Okay, so and the minimization of the redundancy is handled, carry out by dividing the table into a number of relations. That is a single relation into a number of relations and enforcing a relationship between the relations. That is normalization. And so normal forms are simple rules. Okay, so which retains the consistent state of your database. Okay, so rules which are helpful to retain the consistency consistent of your data in a database are named as normal forms. Okay, so in database, so we have several normal forms. Okay, it starts from first normal form, second normal form, third normal form, then comes Boyce code normal form. Sometimes it is known as 3.5 normal form. So followed by Boyce code normal form or 3.5, we'll be having fourth and fifth normal form. So this is the hierarchy. The schematic diagram of the various normal form is projected here. So this is the outermost, okay, outermost structure. So where we have unnormalized relations, okay, and to bring it to first, okay. So by composing our, okay, so by decomposing your table into some number of subtables, we can bring it to first normal form. And to further to reduce the anomalies, we can decompose the relation and we can bring it to second normal form. So like that, we can go through the several forms of normalization. Okay. So it goes up to fifth normal form. Okay. So that is the highest level of normal form. Okay. So first normal form makes that is the entry of a table, that is it maintains the atomic property of a table value. So we will discuss each and every normal form in further session. Okay, so whereas from normalized relation, we can bring it to further normal forms. So in practice, third normal form is considered as the highest normal form in realization. So before to talk about the normal forms, let me introduce key factors which helps us to refine the your database design, okay, through normalization. Okay, so there are two important key terms. One is functional dependencies and keys. Okay, so these two are considered as important key terms concerning your normalization. Okay, so we knew that normalization is a database design mechanism which helps us to retain your table in a well-defined manner. Okay, which removes the redundancy as well as which avoids the inconsistency data in it. Okay, and the functional dependency is the important key term. Okay, and it acts as the formal measure, okay, which brings the goodness of the relational design. Okay, so as I said earlier, yeah, functional dependencies and keys are used to define the normal forms for your relation. Okay, so whereas the functional dependencies are nothing but constraints which are derived from the meaning and interrelationship of the data attributes present in your relation. Okay. Okay, so this is the definition for that is the formal definition for functional dependency. So consider we'll be having a set of attributes X. Okay, suppose the X functionally determines a set of attributes Y. Okay, if the value of X determines a unique value for Y. So we can say the definition in the form of notation: X determines Y. X determines Y in the sense X can be a single attribute or a set of attributes. Okay, a single or set of attributes which determines the unique value. Okay, for the attribute in another is known as your functional dependency. Okay, so this is the condition. X determines Y holds if whenever two tuples have the same value for X, they must have the same value for Y. That is, if tuple 1, that is T1 of X equal to T2 of X, then okay, T1 of Y must be equivalent to T2 of Y in any relation instance, okay, which is captured in the state R of R. Okay, so X determines Y in a particular relation R specifies a constraint on all relation instance R of R. So if these are derived from the real world constraints on the attributes. Okay, so this is the formal definition for functional dependency. X determines Y in the sense a set of attributes which are defined in X determines the values of Y. So here comes the examples. Consider an employee, okay, a company scenario. So in a company, there will be a employee relation, and there will be a project relation, and there will be a department. Okay, so these are so many relations. Okay, which constitutes a company scenario. Okay, so the social security number, okay, in the employee table determines the name of the employee. Okay, so the social security number helps to determine the name of the employee. Okay, in the sense we can say that there exists a functional dependency between a social security number and the name of the employee. So similarly, suppose a project number determines the project name and location. Okay, so in that sense, we can say that P number determines P name and P location. Okay, determines a unique value of P name and P location. In that case, we can derive a functional dependency between these two attributes. Okay. And so one more example is, okay, so consider your employee SSN and the project number determines the hours per week the particular employee works on the project. Okay, so in that case, we can say that the composite attributes, social security number and P number, okay, so these are the set of attributes. So we can say at composite. So this composite attribute determines the value hours, okay, in the works on relation. So these are some examples of what is functional dependency. Okay, so functional dependency and keys. Okay, so a functional dependency is a property of the attributes in the schema R. Okay, so the constraint must hold on every relation instance. Okay, so the constraint must hold, it must true for every relation instance. Okay, so whenever a new tuple is inserted or updated or deleted, the constraint must be true in all such possible operations. Okay, so such constraint is known as functional dependency. Okay, and if K is a key of R, then K functionally determines all attributes in R. Okay, so suppose the attribute which determines the value of other attributes, okay, is a key in the sense we can say that. So that is the key, that is the whole element. So that is the primary element which determines the values of other attributes of R. And this constraint must hold all the time, irrespective of the state. And from the functional dependencies, we can exploit some inference rules. Okay, so which may be used in a further normal forms. When coming to your third normal form, we will discuss about transitive. Okay, so what is transitive? So these are some inference rules which are derived from your functional dependency. Okay, so the functional dependency infers some additional functional dependency that hold whenever the FD is in F hold. Okay, so it satisfies the Armstrong inference rules like reflexive, augmentation, and transitive. Okay, so these reflexive in the sense, okay, if there exists Y, okay, subset of X, okay, so Y is a subset of X. So then we can say that X determines Y because Y is a subset of X. So we can say that X can be used to functionally determine the values of Y. So we can specify a notation or we can frame a notation X determines Y. So that is reflexive. Okay. So if a particular attribute R, a set of attributes would be determined by some other, okay, R. Okay. So there exists an attribute which is subset of another composite attribute. Then we can say that the composite attribute helps to determine this particular attribute. So that is reflexive property. Okay. So next comes augmentation. So augmentation in the sense, suppose there exists dependency between X and Y, which means if X determines Y, then any new augment attribute, for example, X is Z determines, so we can say that suppose I am augmenting one new argument, okay, with X, then we can say that X is Z, okay, which is a combination of X and Z, okay, X, the value of X as well as value of Y, okay, which helps to determine the value of Y and Z because there exists a functional dependency between X and Y, okay, so then a new augmented attribute, okay, will also be captured, okay, in the form of X is Z tends to, that is X is Z determines Y is Z, okay, that is a combined set of X and Z will helps to address the combined set of Y and Z, that is it determines the unique value of Y and Z, okay, so like such constraint is known as augmentation. Then the third important inference rule is transitive. Okay, transitive. If there exists a functional dependency between x and y and z, then implicitly it says that uh, there exists a functional dependency between x and z. Okay, with respect to the transitive property, because x determines the value of y and y determines the value of z. So we can informally form a dependency x tends to z. Okay, so these are the important inference rules which are derived from your FDs. Apart from this, we'll be having some additional as well some useful inference rules. Okay, so decomposition, union, pseudo, transitivity, and closure are the additional inference rules. Okay, so decomposition in the sense, suppose there exists a functional dependency between x and y is it, then we can decompose the relation, okay, as two relations having x and y as one relation and x and z as one relation. So this is known as decomposition. Okay, so if there exists dependency between x with y z, we can decompose this into two tables retaining the functional dependency between x and y and x and z. Okay, that is decomposition. So without losing the data, we can decompose this particular single relation into two relations by applying the inference rule. Okay, then next comes union. Suppose we are having a dependency between x and y and x and z. Okay, then we can use x to determine the value of y z. Okay, so that is union. The next comes pseudo-transitivity. Pseudo-transitivity in the sense there exists a dependency between x and y as well wy and z. Okay, so in that case we can use wx, okay, to determine the value of z. Okay, aligning with transitivity rule. Okay, so this is pseudo transitivity, and there exists a term called as closure. Okay, closure of a set f of fd is the set which is denoted as f plus, which means f plus means closure of functional dependency. So f plus holds all the fd's that can be inferred from f. Okay, so all functional dependencies which are derived from f are addressed as closure. Okay, so these are some other important inference rules. Okay, so let's start with normalization. So before proceeding with normalization, so far we have discussed the facts about the normalizations. The important key terms we must be familiar before proceeding with normalization. So what are the important key terms? It's actually functional dependencies, and these are the important key points because functional dependency and keys frames the constraints or rules. Okay, so that retains the database design. So these are the important key terms. And from the functional dependency, what are the inference rules we can, that is, what are the additional rules we can apply for? Okay, so those are the things we have discussed in previous slides. So now we are going to introduce normalization. Okay. Earlier, the process of decomposing unsatisfactory bad relation by breaking up their attributes into smaller relation is considered as normalization. So in general, normalization is considered as a database design technique which allows us to remove the redundancy. So while removing the redundancy, how we are removing the redundancy? So by following the rule of decomposition. Okay, so through normalization, what we are going to do now, we are going to decompose the relation, okay, into some smaller relations. Okay, so that is normalization. Okay, so by decomposing your relation, that is unsatisfactory bad relation design, by breaking up into some smaller relations. Okay, so we can obtain a better design, okay, which allows flexibility in accessing the data in database. Okay, and the normal form are conditions, okay, which uses keys and FDs of relation to certify whether the relation schema is in a particular normal form or not. Okay, so here your second normal form, third normal form, BCNF, that is boys code normal form, are based on keys and FDs of relational schema, whereas your fourth normal form is based on keys as well. It works on multi-valued dependencies. Okay. Suppose we are having an unnormalized relation, so which has a repeated data. Okay, repeated data in a column or a tuple. Okay, so that is considered as an unnormalized relation, which means so you are having a redundant data in your redundant data present in your table. So you have to refine it. Okay, so to reduce the redundancy, you have to opt for normalization. Okay, so consider your table is in unnormalized form. So consider the example. Here comes the example. So here, this is hospital management system. So here, so we are having attributes. In this particular relation, we are having attributes like patient number, surgeon number, surgery date, name of the patient, address of the patient, followed by name of the surgeon, for what issue and the particular patient has undergone the surgery. Okay, so what are all the post that is your post surgery drugs prescribed, and is there any side effects encountered or not? Okay, so these are the attributes of this particular relation. Okay, so here, so we can see that so there exists a redundant data. For example, so here consider the first tuple for the patient named John White. So he has undergone a surgery for gallstone removal as well kidney stone removal. Whereas gallstone removal will handled by Beth Little. Okay, he's a surgeon who performed the surgery, gallstone removal. Whereas Michael Diamond is another surgeon. So there exists two surgeon entry for one particular patient. Okay, so here comes a redundancy. So this is where a redundancy occurs. Okay, so similarly, Bethlight is a surgeon who has treated the patient named Holcan and Paul Kosher. Okay, so there is Beth Little treated Paul Kosher for the problem of gallstone removal. Okay, so here we can see the redundant, that is the presence of redundant data. Okay, how we can resolve the redundancy? How we can reduce the redundancy? By using the first normal form. So the first normal form prescribes that each relation must contain only atomic values at each row and column. There should be no repeating groups. A column or set of column is called a candidate key when its values can uniquely identify the row in the relation. Okay, so there shouldn't be no repeating groups. Each row must have atomic values. Each row and column must have atomic values, single. Okay, no composite, single atomic values. So here, so we have normalized the unnormalized relation into the first normal form. Okay, by making atomic value entries. Okay, atomic value entries in each and every attribute. Okay, so here it holds one unique value. Okay, for a particular tuple. Okay, so we have splitted John White. Okay, because he undergone two different surgery by two different surgeons. So the single tuple is decomposed into two tuples. Okay, so likewise we have normalized the thing. Okay, so according to first normal form, there shouldn't be no repeating groups found. Okay. So we have fine-tuned, okay, our relation. Okay. So is there any problem? So the first normal form arises the anomalies, okay, like, yes, there exists a problem. I cannot insert a new patient who not yet undergone a surgery. So until the patient not yet undergone a surgery, I cannot enter the patient information into the table. So that is anomaly considering your insertion operation. And one more insertion anomaly, example for insertion anomaly is, suppose a surgeon is newly hired and he has not operated yet. Then there will be no choice to include that particular surgeon into the database. So these are the examples for insertion anomaly considering your first normal form. And here comes the example for update anomaly. If a patient comes in for a new procedure and he has moved to some other location. So we need to change the multiple address entries. So wherever there exists the address entry in your maintained in your relation, we have to make a change over all the respective places. So this is anomaly concerning your update operation. Okay, and with respect to deletion, we cannot delete a patient. Okay, because so by deleting the information of patient also removes the information about surgeon. Okay, and because there exists a functional dependency. So, the first normal form, okay, produces some anomalies, okay, with respect to the insertion, deletion, and scope for insertion, deletion, and update operation. So, to overcome these anomalies, we can move to the next normal form. Okay, so the next normal form is named as second normal form. Okay, and you can say a relation is said to be in second normal form when every non-key attribute is fully functionally dependent on the primary key. Okay, so every non-key attributes must be determined only through the primary key. Okay, so that is the constraint for second normal form. Okay, so is this in second normal form? So according to second normal form, what is the constraint? Every non-key attributes. So here, patient number and surgeon number acts as your primary key or key attribute. Okay, so the patient number, that is the combination of patient number and surgeon has to yield the information about all other non-key attributes. Okay, so whereas the combination of patient number and surgeon number is able to yield the values of only surgery date, patient name, patient address, surgeon name. Okay, so whereas the drug administration and side effects cannot be captured through these things. Okay, so this is not in second normal form. Okay, so to bring it in second normal, a relation, okay, our previous relation like this. So we are holding patient number, name, and address in one relation, and surgeon number, name, and another relation, and we are making use of patient number and surgeon number to determine the value of surgery date, that is surgery information. Okay, pre and post surgery procedures. Okay, so we are breaking our table into three. Okay, one holds the patient information alone, another holds the surgeon. Okay, so because so what are the anomalies we have? That is, we can't enter a patient. Okay, so without the particular patient has undergone a surgery, isn't it? Whereas according to second normal form, by breaking the table into three subtables, okay, we are maintaining a patient information as separate, and this surgeon information is separate. Okay. So that's why we can add a new patient. So with respect to second normal form, now we can add the new patient details as well as new surgeon details. So without attempting a surgery. Okay, so we can add. So insertion anomaly is removed. Okay, so whereas considering our second normal form, if Charles Brown dies, the corresponding tuples from patient and surgery tables can be deleted. So without losing the information on David Rosen, that is, we can retain the surgeon details. Okay. So without losing surgeon information, we can delete a particular patient record. Okay. Likewise, if John White comes in for third time and has moved, we only need to change the patient table. That is, the address entry is retained in only the patient table. So we need not to apply the changes in multiple places. So all the anomalies what we have dealt in first normal form is removed. Okay, by opting the second normal form. Okay. So, is there any new anomalies? Okay, is there a scope for any new anomalies with respect to the operations? Okay, so let me discuss. Okay, so considering a second normal form, we cannot enter the fact that a particular drug has a particular side effect until it is given to until it is tested with the patient. Okay, so that is the first. That is example for insertion anomaly. Okay, and with respect to deletion, if John White receives some other drug because of penicillin, okay, rash, and new drug and side effect are entered, we lost the information that penicillin could cause a rash. Okay, so that is example for a deletion anomaly. Okay, and concerning update, if drug side effects change, we have to update the multiple occurrences of side effects. Okay. So your second normal form also introduces some new anomalies. Okay. So to overcome this, we are moving into the third normal form. Okay. So according to third normal form, we can say a particular relation, okay, is said to be in third normal form if there is no transitive functional dependency between non-key attributes. Okay, which means when one non-key attribute can be determined with one or more non-key attributes, that is said to be transitive functional dependency. Okay, so the side effect column in the surgery table is determined by the drug administered. Okay, the side effect is transitively dependent on drug. So surgery is not third NF. Okay, as it retains the transitive dependency, the surgery relation is not in third normal form. So to bring it into third normal form. Okay. So this is your surgery table. So in surgery table, we have patient and surgeon number, which is a key attribute. So by using it, we can identify, that is, we can determine the value of surgery date, surgery, drug administered, and side effects. Okay. So the drug administered is itself enough to yield the value of side effect. Okay. So there exists a transitive dependency. So to remove the transitive dependency, we have to split the surgery table. Okay. We have to split the surgery table into two. Okay. So the first composes, the first table has attributes patient number, surgeon number, surgery date, surgery, and drug ad. Okay. So whereas the second has drug admin and side effects. So here drug admin is a foreign key which refers the value in drug admin in your this table, surgery table. Okay. So likewise we can decompose. So by decomposing it, we can resolve the problem. Okay. we can resolve the problem. Okay, now we can enter the fact that a particular drug has a particular side effect in the drug relation as well. While removing John White, okay, as says that he received some rashes, okay, issues when using the penicillin as a post drug. Okay, so by removing that information, okay, the information on penicillin and rash is maintained. So by removing John White, we can able to retain penicillin causes rash. Okay, so that information we can retain. Okay, upon removing John White. Okay, in surgery table. Okay, and the side effects for each drug appear only once. Okay, so the update anomaly is also removed. So by bringing into third normal form, that is by decomposing your surgery table into two different relations, we can avoid the anomalies what we have encountered in a second normal form. Okay, is there scope for new anomalies? Okay, is all let me discuss. Is the complete normal form? Okay, so there wouldn't be much deviations. So the third normal form, okay, is considered as the highest level of a normal form. Okay, so to maintain your database design in a consistent way, so you have to apply up to that is, you have to enforce the constraints which are specified up to third normal forms. Okay, so further you want to fine tune your database design means you can apply and you can go for the higher level normal forms like Boyce code and your fourth normal form and fifth normal form. Okay, so let me discuss about the third normal form, that is the 3.5 or Boyce code normal form. Okay, so most 3NF relations are also in BCNF relations. Okay, a 3NF relation is not in BCNF if only the candidate keys in the relation are composite keys. Okay, if the candidate keys are composite keys means, okay, so your third normal form is not in BCNF. Okay, so to be in BCNF, okay, you are according to BCNF, okay, so that shouldn't be any composite key to be used as a candidate key. Okay, so if there is more than one candidate key in relation and the keys are disjoint, that is, some attributes in the keys are common, which means the attributes in keys are common, then it leads to anomalies. So the candidate key must be single attribute. It should not be a composite attribute according to Boyce code normal form. Okay, so your determinant must be a single attribute. Determinant must be a single attribute. There shouldn't be any place for composite attributes. That is Boyce code normal form. Next comes fourth normal form. Any relation is found to be in fourth normal form if it is BCNF, that is Boyce code normal form, and any multi-value dependencies are trivial. Okay, that is, and the presence of multi-value dependency is removed. Okay, in that case, so if a relation is found to be in BCNF and there exists no multi-value dependency means we can say that the relation is in fourth normal form. Okay, so to bring your relation into a fourth normal form, you have to eliminate the non-trivial multi-value dependency by projecting into simpler tables. That is, by decomposing it into some simpler tables to avoid multi-value dependencies. Okay, and the next normal form, the next high-level normal form is named as fifth normal form. Okay, A relation is said to be in fifth normal form if every joint dependency in the relation is implied by the keys of the relation. Okay, so every join, okay, has happened only through its keys. Means we can say the particular relation is in fifth normal form. Implies that relations that have been decomposed in previous normal forms can be recombined via natural joins to recreate the original relation. Which means if we are in a position to combine the decomposed relation into a single relation without losing the information through natural join, means we can say that the particular relation is in fifth normal form. So fifth normal form insists non-loss, that is non-loss decomposition. Okay, it insists on lossless decomposition. Okay. Okay. So we discussed the effectiveness and efficiency issues with your DBMS. So in DBMS, we can store the data in the form of table. Okay, relational model in the sense informally it represents a table. Okay, so table in the sense we can formulate or we can represent the data in two-dimensional form, that is rows and columns. Okay, informally rows and columns. Okay, formally we can say tuples and header, column header, tuples and attributes. Okay, tuples and attributes. So any column in a relational database can be searched for values. Okay, so to improve the efficiency indexes, we can use the storage structures like B trees and hashing. But many useful functions are not indexable and require a complete scan of your database. It requires a complete scan of your database. Means that, so to extract a particular tuple from your database, we can use index. Okay, to enable a fast search, we can use index by deploying the storage structures like B plus R hashing mechanism. Okay, so whereas so many functions are not indexable. So in real world, many functions are not indexable. That requires a complete scan of database for its implementation. So whereas we can improve the efficiency through indexing. Okay, so here consider the text field as an example. So in a conventional RDBMS, when a text field is indexed, only exact matching of the text field contents, okay, or greater than and less than would be retrieved. Okay, can we search for individual words using pattern matching? So to search for individual words, we need a complete scan. We need a full scan. Okay, so text searching is still done best by specialized text search programs like search engines. So in search engines, we used to provide the keywords. So the keywords finds the match in your website and it returns or it retrieves the respective web page. Okay. So normalization is used to perform to reduce or to eliminate the anomalies with respect to insertion, deletion, and updates. Okay, update operation. So, however, a completely normalized database may not be the most efficient or most effective implementation. Okay, so denormalization is sometimes used to improve the efficiency. Okay. So if you are fine-tuning the database design with normalization means to extract a particular information from the database, okay, requires more time. Okay. Uh, so to avoid such demerits, sometimes we opt for denormalization. Okay, so that's why we limited that. So a relation can hold up to third normal forms. So if you are opting a better design by imposing the higher levels of normalization means it complicates your database design as well. It improves the extraction, that is data extraction or query time. Okay, so the completely normalized database will not be considered as the most efficient one. So in normalization, we used to split the database information across multiple datas. So we used to break the table into some smaller tables, isn't it? So we used to split the database information across multiple tables. To retrieve a complete information from a normalized database, the join operation must be used. Okay, so considering your SQL domain, join tends to be expensive in terms of processing time, and very large joins are very expensive. Okay, so that's why we are saying that the complete normalized design leads to expensive processing time, because in normalization we have divided and we have break the relation into a number of sub relations, and to infer a particular information from the relation, so we have to check with all the divided sub relations, okay, to infer a particular information, okay, through query. So we have to join the break up smaller relations into a single component to infer some information over it. So to combine, we have to apply the join. Okay. So with respect to SQL, all other commands, join tends to be expensive because it consumes more processing time. Okay. And you have decomposed the table into some n number of tables, means we have to apply some large joins to bring a unified relation. So it leads to very expensive processing time. So a complete normalized relation will not be considered as an efficient solution. So we can limit our normalization with some third normal form. Okay, that's enough. So here comes the examples for downward, that is denormalization. Okay, so before we have customer and order relation. So the customer relation has attributes ID, address, name, and telephone number. Okay, which, and the order has attributes order number, data taken, date dispatched, date invoiced, and the customer ID. Okay, so which retains the 1:n relationship. Okay, customer and order has 1:n relationship. Okay, so here, by applying denormalization, we are equipping the order table with the customer name as additional attribute. Okay. This is upward normalization. That is, so where we have order number, item number, and item price and num order. Okay, as elements of, that is, attributes of order item. Okay, so whereas order number, date taken, date dispatched, and date invoice, customer ID, and customer name. as the attributes of order. Okay. So here, by applying denormalization, your order table now contains the attributes like it retains order number, date taken, date dispatched, date invoiced, customer ID, and name. In addition to that, it retains the order price. Okay, it retains the order price. So we are applying the denormalization in general to improve the query speed. Okay, so the query speed is improved at the expense of more complex or problematic DML, that is data manipulation language. So you can improve the query speed, okay, by using a simple DMLs, okay, instead of applying a more complicated or problematic DML, okay. So denormalization helps us to improve the query speed, whereas normalization helps us to reduce the redundancy. Denormalization helps us to improve the operation speed. Okay. So, shall we have a quick summarization on normalization? I think so. You grasp something about normalization. So here I will go through the slides in a quick manner, because normalization is considered as a core topic in database management system. Okay, you must be very familiar about the normalization. So through relational model, okay, so we can represent a data into two-dimensional table form. Okay, so which provides a flexible way to work with. Okay, work with the data. Okay, so whereas there exists a number of there arises a possibility for redundancies. Okay, so the database design must avoid the redundancies. That is the duplicate entries, okay, the multiple entries. Okay, so to avoid the redundancy, we can go for the database design technique, which is normalization. Okay, and the normalization helps is a mechanism, or we can say that is a data organizing technique that helps us to remove the redundancy from your relation, and it maintains the consistency of the data. Okay, so to retain the consistency of the data, your normalization uses some inference rules. That is, your normalization uses some constraints. By enforcing the constraints, we can maintain the that is, we can avoid the redundancy, and we can maintain the consistency of data. Okay, the constraints are specified via normal forms. Okay, so in database we have first normal form to 5 normal forms. Okay, so we have first normal form, second normal form, third normal form, then 3.5 are Boyce code normal form, fourth normal form, and fifth normal form. So these are the various normal forms. Means each normal form enforces a constraint. Okay, so by enforcing the constraint, we can reduce the redundancy, as well we can address the anomalies which can encounter through the manipulation operations like insertion, deletion, and update. Okay. So, this is it. Okay. So, your first normal form, that is your first normal form ensures that all the attributes must have atomic values for it. Okay, so all the attributes, okay, in a relation must have atomic values. So that is the constraint of your first normal form. And what is the constraint for your second normal form? That shouldn't be any partial functional dependency exist between the attributes, which means that every non-key attributes must be determined only through the key attribute. Okay, that is the second normal form, the constraint of second normal form. Okay, and what is the constraint of third normal form? According to third normal form, there shouldn't be any transitive functional dependency. Okay, so the non-key attributes should not be determined by any of the non-key attributes. Okay, so that is that shouldn't be any transitive functional dependency. That is the constraint for your third normal form. Okay, so to bring your relation into second normal form, first you have to ensure the first normal form. Okay, so first you have to ensure each and every attributes of your table has atomic values or not. Okay, so by ensuring the first normal form, we can check for the functional dependency. If there exists no partial functional dependency, means we can declare the particular relation is to be in second normal form. Okay, and to declare a relation is in a third normal form. Okay, so it has to ensure the constraint of first normal form as well second normal form. Also, it should not have any transitive dependency. Okay, then next comes the Boy's code normal form. So the Boy's code normal forms says that the determinant must be that is your candidate key must be a single attribute. Okay, no composite attributes are allowed. Okay, and your fourth normal form deals with multi-value dependency, and your fifth normal form deals with lossless join. Is it clear? So these are the various normal forms. Normal forms defines the constraints to be satisfied by your database, or that is a relation. Okay, the collection of relations which constitutes the database. Okay, and for effective and efficient utilization of database, normalization will not be a complete solution. That is, a complete normalized relation will not facilitate a better processing time. Okay, so sometimes it leads to, so we are applying some higher levels. We are fine tuning our database design with higher level normal forms like fourth and fifth normal form. We are ensuring a database design with fifth normal form. Then there may be a chances for higher processing time. So the complete normalized relation, okay, will not be considered as a efficient one by considering its processing time. So we can apply we can apply the database design up to some minimum level, that is up to third level. Here the third level considered as the highest level. Okay, and so to improve the query speed, okay, so what we have to do now, we have to going for the reverse engine, that is denormalization. So denormalization helps us to remove the that is to join the break, that is to join the tables which are breaked, okay, which are decomposed, okay, through your normalization into one. So here the join takes or consumes much query, that is much processing time. Okay, so to infer useful information from your relation, okay, it takes more time as your relation is splitted into multiple tables, as the data of your database is split across multiple tables. Okay, so that's all about normalization and denormalization. Once again, I'm repeating. First normal form ensures the atomic values for the attributes. The second normal form ensures there shouldn't be any partial functional dependency. Partial functional dependency in the sense every non-key attribute needs the full primary key for the unique identification. Okay, so every non-key attributes must be determined only through its primary key. Okay, that is known as fully functional dependency. So second normal form insists fully functional dependent. Okay, and your third normal form should avoid the transitive functional dependency. Okay, that is when one non-key attribute can be determined with one or more non-key attribute, then it is said to be a transitive functional dependency. So like such transitive functional dependency should not be there in your relation. Okay, to make your relation is in third normal form. Okay. Boy's code normal form. Every determinant must be a candidate key, and the candidate key must be a single attribute. And the fourth normal form deals with multi-value dependency. You have to eliminate the multi-value dependency by projecting your table into some subtables, some smaller tables. And fifth normal form ensures the lossless join. A relation which is in a position to come back to its original relation, okay, after its decomposition states via natural join without any loss of data is said to be in fifth normal form. So normalization is used to reduce the redundancy by decomposing your table into some smaller tables. First normal form insists atomic values. All attributes must be atomic. Second normal form insists on fully functional dependency. Third normal form must disallow transitive functional dependency. Your fourth Boy's code normal form insists that every determinant must be a candidate key, and candidate key must be a single attribute. Okay, and the fourth normal form deals with your multi-value dependency, and fifth normal form deals with lossless joins. So normalization is an important topic concerning your database management system. And there will be a definite questions on normal forms, normalization. Okay, so you may ask to check whether this particular relation is in first normal form or second normal form. Okay, or you can ask to verify the constraint, whether this particular constraint is enforced, okay, or not. Okay, so there must be a questions on normalization in your GATE exams. So this is very much important topic. If you have no queries, thank you all. Is there any queries? If not, thank you, students. Thank you for your patience listening, and don't skip the topic. So this is very much important topic. Thank you all.